possible, very likely, you have two options. You can reduce your step amplitude, because in the objectives we tell you to move a step command, but we don't tell you how much you have to move. So in order to stay within the limitations of the motor, you can reduce the amplitude. Then the motor doesn't have to work as hard. Or you can adjust your gains and bring your gains down, especially your proportional gain, which is telling it to go too fast. You can reduce that down, and now you can get back to that 0.3 radians without exceeding 5 volts. So those are your design constraints. This is a design problem for an engineer, very typical in aerospace systems. To design a system, to do performance based on your limitations and how much friction and what the motor voltage can do. Okay? Kind of makes sense? Any questions? I know you'll have more questions. We have a lot of people here to help. The lab assistants are always really excited about this lab. This is one of their favorites. Bobby and I also are very passionate about this lab. Chris, and also the TAs who've run through it with us yesterday. So I know that was a lot of information. That's okay. You'll have a lot of questions as we go through this. Please ask them. We're happy to talk to you about it. Another thing I want to mention to you is the control system is not being run in LabVIEW. The control system is being run on the MyRio, which is local to the spacecraft. So imagine the computer and the LabVIEW interface is just your ground station. Your ground station is sending position commands and then reading back the performance position of what actually occurred. But it's not doing any of the implementation of the control gains, and all of that math is not happening on the ground station. It's happening on the spacecraft. So if I unplug the LabVIEW computer and just unplug its data line, it's just going to keep doing its control system, because that's what I last told it to do. I can no longer update. I've lost communication with my satellite. My ground station is now disconnected from my satellite, and it just keeps doing its thing. So I mention this because it's important. If it goes unstable and you leave an unstable controller loaded onto the spacecraft, it will continue to be unstable until you give it a new command. Okay, so that's an important thing that I want to point out of where the control is actually happening. All right, now we'll plug our ground station back in so we can send new commands. Another reason why it's important to shut it down properly. Just closing out the LabVIEW program and Xing it out might leave the controller on there. It's just going to keep running until you power cycle, because we programmed in for it to restart from 0 once we power cycle the unit. Okay, so a couple of things I want to mention here. This switch, the enter values for the gain constants, this is a toggle switch. If you toggle that, you can use the default values, which are built in, or if you toggle that over to enter values, now you're allowed to control and enter your own values. So that's what that switch does. You can also control the step amplitude, how far in degrees, actually in this case we do radians, how many radians do you want it to move? And then you can also control the step duration. How long does it stay at that position? So does it stay at that position for 10 seconds, 5 seconds? You want to give it some time to stable out. So in case it oscillates, especially with the flexible arm, it might need some time to damp out before you switch to the next position. So you can adjust those values as needed for the step duration based on just your observations. Then once you get gains that you're happy with, that you want to take some data on so you can analyze, you want to hit the Save Data button. So that Save Data button, you want to select that. That's going to ask you where you want to save your data. So we have folders in there for each of the 3 sections for you to save your data in. and you will not be saving this data to share as a class. It's just for you and your group. So you can call it whatever you want. There's no naming convention because we don't need to share data. And then say OK, and it'll say that. And this is your desired data size. So your desired data size needs to match up with your step duration. If I have this set to 1 second and my step duration is 5, I'm not even going to get an entire step of data. That would be useless. So you want to make sure that your data size is probably at least 2 or 3 times larger than your step duration, so you can get a couple cycles in the data file. Okay?
You point out that the data is saved.
Yes. Thank you, Bobby. So the data that is saved is not save data and then save future data. It'll save the previous 10 seconds in this case. So when it looks good on the screen, then you hit save data, it'll save the previous 10 seconds that you saw on the screen. So that's an important point. It's important to get a couple of cycles. It's also important to keep track of which unit you're using, because each of the units acts a little bit different. They have preferred direction. Some of them track better on the left side versus the right side, or vice versa. And you can use whichever side matches better. So if it tracks better going to the right, like in this case, it's tracking a little bit better going this direction, I would choose to extract this data set and ignore the data set going in the other direction. Okay? Let's see, what else? Let's talk about the flexible arm really quick. After you've gotten real comfortable with the rigid arm in the next week or so, then we're going to also start moving to the flexible arm. And this is where the dynamics in the equations get a lot more interesting. So doing the rigid arm is really kind of pretty basic. Doing the flexible arm now is really more representative of what you'd see in a real spacecraft. Most of the time our solar panels are not going to be rigid. They're going to be flexible. And if we move them too quickly, we could bend them so much that the solar panels are actually going to crack and break. So this is where the control gains and the performance are really important. We want to be able to point it towards the sun, but not have it overshoot or oscillate too much to break the solar panels. So this is where your equations are going to get really interesting. Now we have 2 sensor feedbacks. We still have the same potentiometer for angle of the hub. That's our hub angle. So that's our pointing position. But we also now have a sensor to tell us how much is the tip deflecting. Because I do not want this tip to bend too much or my solar panel is going to break. So the tip deflection is read out here in meters. So that's how many meters this tip has deflected in this perpendicular direction. We measure that with strain gauges. The strain gauges are placed at the base, which is where the point of maximum strain occurs in a bending beam equation. So if you think back to your bending beam equations, the more I bend this, the more strain I get right at the clamped point. So that's why the strain gauges are placed here. They are extremely fragile and extremely expensive, so be very careful with them. And also the wires coming from them, that they don't get broken. We have some physical stops here, so that if it gets too unstable, it can come around and hit those stops and not rip off the wires. But we still need to be careful with it, which is why we're not going to play with unstable gains on this unit. Let's go ahead and look at, actually I don't want to hook it up because it'll take too much time. But this one is using the strain gauges fed back through a conditioning board and then sent to the same MyRio. So it's just an add-on to the rigid arm with additional features. This extra sensor gives us 2 more gains that we can play with. So if you can select Unit 4 Flexible, just to show how those gains show up. Now we have PD control of our hub angle and PD control of our tip. So we have our proportional gains and our derivative gains for each. They're labeled here, K1 through K4. Then we also have these plots, which have our tip deflection and our tip velocity. So tip deflection is measured from the strain gauges, and then that deflection, called little d in your equation, is also taken the derivative of to get d dot, which is your tip velocity. And now we can apply gains K2 and K4 to control how the tip is operating as well. So if the tip is deflecting too much from 0, that K2 proportional gain will bring it back to 0. If the tip is moving too fast, that velocity will be reduced by the tip derivative K4. So now we can actually make this flexible arm operate like a rigid arm. And we'll have you play around with, what if you just put gains in here and don't have K2, K4? How does it work? You'll see how much it oscillates because we don't have that feedback on the tip. And then once you implement K2 and K4, you can see how you can reduce that tip deflection down to almost 0. Also, the strain gauges are extremely sensitive. They're so sensitive that they can actually see the little air currents of the tip as it's moving. So you'll see that this tip deflection never gets perfectly to 0. It's going to oscillate very slightly around 0. And again, we don't have enough motor voltage. You want to? Okay. You don't have enough motor voltage to overcome that slight variation in the tip deflection. So you'll notice in the lab document that we tell you to get the tip deflection down to some plus or minus. You don't have to get it perfectly to 0, because that's not possible. But we want you to get it to within our error bounds of 0. So now you have what's called a single output, multiple input system, MISO. So what we have for feedback is 2 sensors, our strain gauge and our potentiometer, but we still only have the single output, which is our DC motor. All of these gains together, K1 through K4, all add up against their errors. So K1 times the error of position, K2 times the error in tip deflection, K3 derivative, K4 derivative. All of those add up to one motor voltage that's sent to the DC motor. So that control voltage will still be applied to and shown to you, and you have to make sure that that doesn't exceed 5 volts. So now let's use the default gains on this one, Bobby. Oh, they're not actually, maybe they are once you select the hardware. Oh, they're not. Actually, try one more time for the default gain values. Okay, I thought maybe we programmed those in, I can't remember. Okay, all right. One thing I want to point out that kind of trips people up the first time is, remember before when I said negative gains were unstable? There's one exception to that, the K2 gain. K2 gain actually has to be negative in order to be stable. It's reversed of all the other gains. And the reason is, if you move the hub in one direction, the tip is going to go in the opposite direction. Just the way the dynamics work. If I move the root here, the tip's going to go this way. If I move the hub this way, the tip's going to go the opposite direction. So there's an inverse relationship between the hub angle and the tip deflection. So when we go to put gains in, and as you're calculating gains, K1 will be positive, K2 will be negative, K3 and K4 will be positive. Because the velocity, we still want to have proportional to positive velocities. And derivative K3 is always positive, because it was before. The only one that needs to be negative is K2. If you put in positive gains for K2, that's now unstable. So it's the inverse relationship. And that's just due to the dynamics of the system. Now that we have this plugged in, you can see that the strain gauges are very accurate and really sensitive. So they've tried to actually measure all of these little deflections. Even right now, looking at it, you can barely see this moving just because of the air currents. And each of the units is going to be a little bit different. So again, it's important to know which unit you're doing. Let's just do a quick test to wrap it up. Let's do a step position of 0.3. Yes. So for this, the clear ground for the emergency stop. Okay. Okay. So when the strain gauges start up, they're going to have a little power applied to them, and that's going to cause an offset. That offset needs to be taken out in the software. So you can see this isn't oscillating quite around 0. It's close, but it's a little bit off. We can fix that offset by hitting the escape or the emergency stop. That'll reset the hardware, so it'll re-zero, and then start it again by toggling back. And now we'll be oscillating a little bit better around 0. Now we can show, let's actually do like 5, let's do a step response of just 0.3, and we'll just do proportional. So you can see how bad it oscillates. Without any feedback control, you can see that this system is clearly not critically damped. It goes to where it's trying to go, and then it oscillates, and then eventually damps out. So this is the natural damping ratio of the system. That's how long it takes for it to damp out with any control, without any control system added. But you're going to improve upon that by adding in these tip derivative gains, so you can damp out that tip deflection, so it doesn't oscillate so much and it just gets right to where it's supposed to go. And you can see that here as well, that the base is oscillating and not reaching and tracking that square wave. You can improve upon that with your control gains that you're going to design. Question? Any questions? Okay, I tried to cram a lot of information into a small amount of time. We did record it, so please look back at the video if you have any other questions. You can go back and look at what we said. Also, we'll be available for questions. Now we'll go ahead and take our groups. Oh,
One more.
actually, go ahead.
So one other limitation we have here has to do with the derivative and how that's being calculated. So we're taking the derivative just from the position sensor. So you can see once this chart zooms in a little bit that there's some noise on that. So when you take the derivative of the noisy signal, that noise basically becomes amplified or carried over onto the derivative portion as well. So then when you apply a gain to that, then your velocity contribution could become noisy, and then that is another contributor for the physical limitations here with regards to the instability, with regards to the noise. Okay? Does that make sense? Maybe we can take the step off and just do the whole position. So you can see how noisy this hub velocity is, even when we're not moving. So you apply a gain to that, and that noise just then gets fed back into the motor controller.
So that's why large derivative gains are not feasible because of the noise. I think that's it. All right.